Okay, quick look at this. So the ring problem. Okay, so here's an example of the ring problem. So two ropes pull on a ring. One exerts a 91.6 Newton force at 238 degrees relative to the positive x-axis. The other one 16.8 newtons at 138 degrees, right? So here's a picture, right, that would represent that. Everybody see that? So 138 degrees is going to be 42 degrees less than 180, right? So I could make this my 42 degree angle, right? And I could break this vector up then. I could break that vector up into the 16.8, I could break it up into components. Right, so there's going to be one component, the horizontal component, and there's going to be the vertical component, right? What about the blue vector? So I could make the blue vector, I could break that, I could use either angle, but if it's, I could either use this acute angle or that acute angle, but if it's 238 degrees total, that's 32 degrees less than 270, right? Which would be 3/4 of the way around the circle, 3 times 90. So then I could break that one up into a vertical component and a horizontal component, right? So what would be the magnitudes of those? If I, is this one, the vertical component of the red vector, is that going to be a sine or cosine issue? It's going to be a sine, right? So that's going to be 16.8 sine 42, right? And this guy down here is going to be 16.8 cosine 42, right? That bottom one. Everybody agree? Okay, how about the components of the blue vector? So we're going to get the vertical component, sine or cosine? Cosine. So 91.6 cosine, 32 degrees. And then down here, we're going to get 91.6 sine 32, right? And so all we're going to do then, if we want to know what is the magnitude of the net force, right? That's it for the first part. So we just have to add those up. Just make a little table, right? That's all we're doing here is we're making a table, just like we did back in chapter, like, I don't know, 4 or something. Remember we did a lot of this vector resolution stuff. And so we've got the vector column, we've got the x component column, and the y component column. And that thing's down there. Get out of there. Go away. Okay, so then how about the blue vector? We'll just call that vector B.
Are you recording this?
I am recording this, yes. Actually, let's do the red one first. So the red vector we'll just call red. What's the x component then?
It's the cosine.
Okay, it's cosine. What's the sign going to be of that? The SIGN sign. Positive or negative?
Oh, negative.
Negative, right? 'Cause it's pointing in the negative x direction. So I'm going to get negative 16.8 cosine 42, right? How about the y component? Positive or negative?
Positive.
That's going to be the sine, right? 16.8 sine 42, just calculator numbers. Okay, how about the blue vector? X component, positive or negative?
Negative.
Negative 91.6 sine, right? Sine 32 degrees. Y component? Negative, right? Negative 91, because it's pointing down. Negative 91.6 cosine 32, right? So all I've got to do then is just to get my resultant vector. To get my resultant vector, I just have to sum those. I'm going to add up the x components and the y components of all the vectors to find the overall x component, right? The net x component and the net y component. So these are just calculator numbers. So let's throw those in the calculator. So negative 16.8 cosine 42. We're doing the x column, right? Minus 91.6 sine 32 gives us that number. So that's a calculator number. It's roughly equal to negative 61, right? We got the calculator number there, though. Okay, let's do the y component. So all I've got to do to get the y component, I'll just go back up and edit that line. And it should be, let's go second left. I'm going to go ahead and delete the negative sign because it's positive 16.8 sine. Got to make that a sine, 42. And then minus 91.6 cosine. So I'll change the sine to a cosine. Hit enter. And we get about negative 66. Right, so then all I've got to do is just build my resultant vector out of those components, right? So let's draw those. Okay, so then I've got my x component is negative 61. The negative just tells me what direction it's going. It's going to the left, right? So that's going to be something like that. Right? And we've got the calculator number there in our calculator. The y component, I'm just going to add those tip to tail, right? The components. The y component added tip to tail, that goes down 66. So the negative just tells me it goes down. And then this is going to be the resultant, right? I just need to know what that is. Okay, so if I want to find out what the magnitude of that is, what do I do? Pythagorean theorem. Okay, and I've got my calculator numbers. So I'll just do the absolute value, the square root. The square root of this number squared, but it's negative, right? So I got to be careful. So either I have to enclose it in parentheses first or absolute value. I'll put it in parentheses. So I've got the square root of that number. Because it's negative, I put it in parentheses before I square it, plus that number in parentheses squared. And that gives me 90.2, so and I think I want 3 sig figs, right? So about 90.2. Is the magnitude, right? And then I got to find theta. Well, that's not really theta, is it? Theta's got to be measured all the way around from there. But I'll just add 180 to that one, right? Everybody see that? Okay, so how do I find that theta? It's going to be arctangent, right? Because I've got to do that angle is equal to the tangent, or the tangent of that angle equals 66 over 61, opposite over adjacent. So that angle must equal the arctangent of 66 over 61. Okay, so we'll go inverse tangent of now I want these numbers to be positive, right? So what could I do to make them positive? What could I do? Take away the negatives. Okay, I could. That's fine. I could use absolute value, right? And that's kind of a good little trick on here. when you want to just discount the sign, quickest way to get to absolute value, or a really quick way, is if you just hit the math button and go to scoot over one to the right to the number menu, and it's right there, absolute value. So I could do the absolute value of that number's the opposite one, right? That number divided by absolute value of the 61, because opposite over adjacent, right? Okay. Close it. And it gives us back 47.4. So if that's 47.4, what am I going to do to get my angle? I'm going to add 180 to that. Good. So plus 180 is that. So I get about 227 to 3 places. Okay. And if we go up here, let's just see what we got. So 90.2, is that what we had? Oh, yeah, 90.2. And the angle is 227. Okay. So then the other ones are going to be, I don't have to do any work at all, do I? Because that's the net force of those two forces that are acting. The other part of the question wants to know, to put those into equilibrium, what third force would we need? It's going to have to be one that completely cancels that net force, doesn't it? Right? Because all three forces, for all three forces to sum to 0, they have to cancel each other out, right? So what's the magnitude going to be? 90.2. What's the angle going to be?
That one minus 180?
That one minus 180. And so on our calculator, what was that? If I took my calculator number and I subtracted 180, I had 47.4. Everybody agree? Okay, because I got to have it out to 3 sig figs. So there it is, 47.4. Right? That is by far the problem, and that surprises me. That's not the one. That's the way it was last time too. Here I made that one worth 30 points, thinking that was going to be an easier one, and that's the one that's causing most people the most trouble.
Yeah, that's the one.
Is that one? The harder ones people are getting, and that one that I thought was going to be an easier one ends up being, I don't know. I guess I can see why. I mean, there's a lot of stuff involved there. Just got to be kind of careful with it. Okay. Does that help? Okay. And then the other one you were asking about was which one, Cade? The puck one, and that's on the second test, right? Okay, so I'm not going to help much because that one's kind of a bonus one, I think, if I'm thinking of the right one.
What classroom is this already?
It goes down to Mrs. Umbarger. Yeah.
What?
Let's see here. So. Okay, so. Like that one right there. That one's kind of a tough one.
It's only with 2 points.
Yeah,
Is that the one I had?
it is actually.
Yeah, that's like mine. I put it equal 60.
Just a little bit up.
Just a touch, yeah.
That's what I did. I didn't do either of the bonus ones.
Okay, so then what about this? We get this very, very large conical pit. So everybody gets the idea what that is. It's like the pit is just shaped like an inverted cone, right? That's the track. So in cross section, it would look kind of like this. Okay, let's make this a steep angle to exaggerate that 51.1. So this is the pit, right? That's the track. It just goes, I've just cut right down the middle of the track, right? And we want to know how far up the track, so measured along the surface of the track, what distance am I going to have to go up so that a puck traveling at this speed is gonna stay at the same height around the track, right? Does that make sense? Really what this boils down to, doesn't it, is I just need to know, I need to know for what circle, for exactly what circle is this speed gonna match the centripetal acceleration in the radius, right? Does that make sense? How are we gonna figure out what the centripetal acceleration is?
Radius. First equation.
So if I take, like here's the puck traveling around and it's going on this trajectory around this thing. What are the forces acting on the puck? Right? Gravity. And what else?
Force. Oh. Now they go down.
It's gonna be, yeah, the normal force, right? And that's it. There's only gonna be two forces, right? The surface is pushing on, is providing a support force for the puck as it slides around. It's pushing on the puck, and then gravity is pushing down. So we've got this vector up here that's gotta be pretty long, doesn't it? 'Cause it's gotta counteract gravity, right? So this is the normal force. If we break that up into components, we break the normal force into components, we're just gonna get something like this, right? We're gonna get a vertical component and a horizontal component. Well, if this angle right here is 51 degrees, then so is that one, right? The big angle goes with the big angle. Everybody agree? And so what's gonna be the vertical component of the normal force in terms of sine or cosine? It's gonna be a cosine, isn't it? Because that's my theta, so we're gonna get normal force cosine theta, which is cosine 51. And then the horizontal component would be normal force sine 51, right? So really we've only got 3 components to put on our orthogonalized free body diagram, right? We can just take all that complicated drawing and we can just distill it down to, there's my object pointing down. I've got mg. Counteracting that, pointing up is normal force cosine theta. And then pointing to the inside towards the center of the circle. So that's going to be my centripetal force, isn't it? It's going to be normal force sine 51, right? That's it, okay? So then what are my equations of motion I get from that? So I get one equation of motion. What about vertically? What's the net vertical force going to be a sum of?
0.
It's going to add to 0. You're right. But it's going to be what? What am I going to add up to get 0 there? Okay, so the positive, the upward, the positive vertical component is going to be the purple one. So normal force cosine 51 minus, that's going down, right? Minus mg equals 0. So that's just telling us that normal force, if I solve for normal force, what is it? I'm going to add mg to this side, and what else? Got to divide by the cosine number, right? So I'm going to get positive mg over cosine 51. Okay, what's my centripetal component? That's going to be the only, this is the one that's pointing, right? That's the component that's pointing towards the center of this circle, because here's the circular path that this puck is taking, right? So that's the one that's keeping it pushing towards the center, keeps it going in a circle, right? That's the centripetal force, right? So that's the one that's just going to be Fn, so normal force sine 51 is equal to ma by Newton's law, right? By Newton's second law. But the acceleration is centripetal acceleration, right? Okay, so what can we do then to solve? I just need to solve for the centripetal acceleration. What could I do? I got to be able to.
So you have your velocity.
Well, I have my normal force here, right? In terms of stuff that I know or could cancel, right?
Oh, so you just plug that in, you can cross out the math.
Exactly, right, the masses will cancel it.
Yeah.
So if I plug that in, look what we get. If I plug that in, now I've got, mg, I just multiply fractions straight across, right? So I've got mg cosine 51, and on the top, I'm just gonna multiply by sine 51, right? Equals m times centripetal acceleration, and now I could divide both sides by m. And the m cancels, and it should, right? This shouldn't depend on mass. Okay. So then what do we get here? So then we end up with centripetal acceleration equals 9.8 times sine 51 degrees divided by cosine 51 degrees. Right? And so that's just gonna be a number, right? I'm just gonna get some number for centripetal acceleration, right? Once I know what that number is, I can just say, well, I know that centripetal acceleration is v squared over r, right? Well, that's gonna be my speed, isn't it? Right? So really all I'm trying to find is, what's the radius? Everybody see that? So if I solve for r, if I can find out what r is, well then that really, I could turn that into, I can use some geometry here, right? I could make a triangle out of this and say, okay, if that's r, which I know, and I know that this angle is 51, then that angle right there would be 51. Or I could say this angle right here is what, 39? Same thing, right? Doesn't make any difference. I could just call that 39. 39. If that's 39 and that's r, and I know what r is, right? I just found out what r is, then really this is the quantity. What color have I used here? How about orange? So this is really the quantity that they're asking for. How far up the track would it have to be, right? So I could use Pythagorean theorem, or I could use, actually I wouldn't use Pythagorean theorem, I would just use, if this is, call that x, and I know what r is, then what's going to be the trig ratio that relates opposite and hypotenuse? Sine would be opposite and hypotenuse, right? Tangent would be opposite and adjacent, right? So we could say sine of 39 degrees equals r over x, and we know what r is. That's the radius that we calculated down there. So I can solve for x. Right.
Wait, what is all?
So r is whatever we get from this, right? We know what I'm not going to do all the calculator work, but we could plug in numbers and find out what centripetal acceleration is, right? Once I know what centripetal acceleration is, I know v is that 71.6, right? So then I could solve for r and know what number goes with r, and what the numerical value of r is. See what I'm saying? So that's a pretty tough one. But how many points was that worth? I think it was only worth 2 points. Yeah.
Yeah.
So
Yeah, there's no way I would.
I double dog dare you to get it, but it's so that you could get a 98% without getting that one. But to get 100, you got to do a really hard problem. So I know that's a hard one.
There's no way I'd be able to figure that out.
Oh, don't say that. You could.
Go like on my own. Are you kidding me?
Yeah, you could. Sure you could.
I would've
Sure you
gotten
could.
stuck. I think where I would have gotten stuck is where you had on your second equation where you had normal force sine 51 equals MAC. I would never have like guessed MAC would equal normal force sine 51. Like I would never I would have figured that out on my own.
Okay, but
Yeah,
what I want and what I want you to see on this, and I know there's a lot. I mean, that's a lot. There's a lot of stuff going on in that problem. But this part right here, I do want you guys to see that you know, if I start with, and that's kind of a mess now, but if I start with this, remember what this was originally. We only had 2 forces acting on this thing, right? We had a normal force and gravity, right? When we draw our free body diagram, if you think about the circular path that this thing is traveling in, right? If we were just to be able to highlight just the path, right? That's going to be a horizontal circle. Everybody agree? And the center, like through the center of the circle would be this axis right up, you know, right straight up from the bottom of the conical pit. Everybody see that?
Yeah.
Okay, so then if we want to break this thing into the useful coordinates for us would be vertical and centripetal, right? Because it's circular motion. So we want to break this thing up. We want to break this purple vector, the normal force vector. We want to break it up into a vertical component that offsets gravity and keeps the puck from sliding, you know, down or up, right? Does that make sense? And then a centripetal component that's causing it to move in that circle, right? Now, what's going to happen? Well, does that make sense? Okay. So then, we would use this this 51-degree angle to take that normal force vector and break it up into its components. Normal force cosine would be vertical, sine would be horizontal. But then really, we've just ended up with two equations of motion, right? We know that the vertical forces have to add to 0, which is useful because now we can solve for what the normal force actually is in terms of other stuff that's useful to us. Normal force by itself is almost never something we know, right? Normal force we're going to have to calculate. We know it's there because the puck doesn't go spontaneously levitating above the track, accelerating upward, and it doesn't burrow into the track either, right? Does that make sense? Okay. But we know that, so those have to offset each other, but this is the one that we really want to focus on. This centripetal component. The centripetal component of the normal force is the one that has to provide the center-seeking force that makes it go in a circle, right? It could be lots of different situations would require centripetal force coming from different types of forces. If it's a satellite orbiting the Earth, then gravity is providing that centripetal force to bend the arc into a circle, right? If it's a stone on a piece of string, then it's the tension in the string that's pulling that rock towards the center, making it go in a circle, right? In this case, it's actually just the pushing force of the track that's pushing this object towards the center of the circle to keep it moving in a circle. Yes, sir.
So do they send satellites to specific altitudes based on their mass?
Yes. Well, not their mass, their speed.
Or
Their
just
speed.
speed?
Yeah, it'd be independent of mass. But if you want a satellite to go at a certain speed through space, then there's only one altitude it could go at and move in a circle. And what would happen in this case, for example, if we put this thing at the wrong spot? Let's just say we wanted it to go this fast, but we put it too close to the center. Yeah, then it's going to fly up, right? It's not going to move in a circle because in that case, the speed would create too much centripetal force. It wouldn't be the right amount to move in a circle, right? Yes, sir.
So does gravity affect, this is totally not different, but does gravity affect light at all?
Yes.
Okay,
In fact,
so
it's funny you should ask that because that's what we're going to start talking about right now.
saying, like, is it possible to make light travel faster by, like, say, spinning it as close as it could go around a black hole and then shooting it off?
It is not. It is not. One of the bizarre things about light, and we'll talk about this a little bit later, but actually, what time are we out here?
10.
Okay, so we got a little time to start this just today. We'll wrap this up tomorrow. I've been waiting to talk about this. This is so much fun. What's that? Well, you guys can start that anytime you want. Oh, yeah, okay, remind me, we do have to do that. So we're gonna have 4 groups instead of 5. So the question though, about light, this is pretty bizarre. If you were on a spaceship that was traveling, like let's just say, okay, let's say you're walking forward on a bus that's traveling at 60 miles an hour and your buddy is standing on the front of the bus and you throw a baseball to your buddy and let's say you throw it at 60 miles an hour.
You're going 120.
Somebody on the ground would see that ball is going 120, wouldn't they?
What's that?
Isn't it like shooting the baseball backwards when you're going?
Yeah, so that'd be the same thing, like if
Einstein's-
if you throw it backwards at 60 and the bus is going this way at 60, right? Then it's gonna arc through the air to your buddy, right? And he's gonna catch it. He thinks it's going 60 because he's on the bus with you. But somebody standing on the road next to you is just gonna see the ball going up in the air a little bit and then your buddy catching it, right? Agreed? Okay, it's not that way with light. If we're going forward in some spaceship at 95% the speed of light, and I shoot a ray gun forward, and the ray gun is traveling at the speed of light because it's a ray gun, right? Then how fast are the photons going when they hit you?
The speed of light.
Speed of light. That's weird, right? They
Well,
don't.
from
Now they do
outside.
change. The color changes, but that's
So
all the
say
changes.
from somebody standing on the ground or whatever.
So you're saying
Same thing.
Well, you wouldn't be able to see
How
it
would,
so far away.
how would that doesn't even,
so
It doesn't seem to add up, and so what happens, there's some consequences of that that are pretty bizarre. The consequences are because the speed of light is invariant in any reference frame, then that tweaks some things pretty seriously. That means, for example, and this is really the case, does anybody have a twin in here? Or a sibling close in age? You got a twin?
Yeah, raise your hand.
Did not know that.
I didn't know that. I didn't know that.
Thinks it's the same person.
Yeah, no. So, okay, so this is a true story. This is an absolutely true story. And there's a little bit more, it's a little more complicated than what I'm saying. There's a couple little tweaks that we'll talk about when we talk about actually about gravity. But this is a true story. So if, let's just say that starting right now, you got an opportunity to take this interstellar trip. And it's a trip of a lifetime. You get to go out and you get to go out and explore the nether reaches of the galaxy. You're traveling in this really sophisticated craft that's going to accelerate at, let's just say it accelerates at 3 Gs the whole time. Okay, so you get going pretty fast after a short period of time. You're going to go out and you're going to explore the other part of the galaxy, and you're going to come back. And let's just say it takes you 2 years. And your sister, before you left, your sister bought you this really nice digital watch that really takes great time. It keeps perfect time. The battery lasts for a long time. And you're marking down. Even though you're not seeing the sunrise and set and everything, you're marking down the day. So when you get back, it's exactly 2 years to the day when you get back and you land. Okay, you land though, and you're expecting this big party to greet you. Expecting who's your twin?
It's a brother.
Jordan. Okay, so that's your brother. Okay, so you're expecting your Jordan and your sister to throw you this big party, but you're thinking it's going to be some kind of wild celebration party. But they hobble out on their walkers and they want to take you to go play some bingo because they're 104 years old. Because that's how much time actually might pass for them, right? And that's the truth. That's one of the consequences of the invariance of the velocity of light, is that moving clocks run slow. It's called time dilation, and it really does happen. It's absolutely measurable, and it really does happen. Yes, sir.
So would he age?
To him, and you might think, wow, what a great deal. I want to be on that, but it's not a great deal. He doesn't experience any more time. From his perspective, his clock only ran 2 years. He didn't get anything extra out of it, right?
Yeah,
But
but
if
if
you-
it's
He physically aged. He aged 2 years. Because
He'd
his
be essentially traveling to the future.
I'll tell you what, you honestly, everybody in here is a time traveler because you're traveling into the future all the time. Right now, we're traveling into the
Every
future.
moment.
And now we're
It's
here,
just
now we're
that.
still traveling.
What really happens is, and I'm gonna have to take more time with this later, but really what's happening is you're traveling through space-time. And you're traveling through space-time at a constant speed, and it just depends on how much of your trip through space-time is devoted to traveling through time, and how much is devoted to traveling through space. It's a good way to think about it. If you're a photon, the photon essentially does not age, because the photon travels through space-time at the speed of light, and so it never travels through time. It's only traveling through space. All of its constant speed is devoted to traveling through space. The faster you go, the more of your journey is devoted to traveling through space, meaning less of it is devoted to traveling through time. If you're standing still, you're traveling only through time. Yes, sir.
Can we watch Interstellar?
No, we can't watch Interstellar.
So
You guys can watch Interstellar.
so
We can talk about it.
If photons have different masses, how can they all travel the same speed?
Okay, photons have no mass.
Or what do they have?
They have no rest mass. Photons have momentum, which I'll prove to you
So
when we
if
get
they're
into
all
the
at
optics
same
section.
speed, technically they would have to have a different mass, right?
If they had any mass, they could not go the speed of light. They don't have, any object with any rest mass could never go the speed of light because, and we can even do in calculus, we talked about this earlier in the year. You might remember, but when we did limits. As the velocity approaches the speed of light, the mass of an object approaches infinity. And so therefore you could never, I can take a roll, sorry. Hang on, I just thought of this. I'm gonna be like in huge trouble if I don't take a roll.
Gone. Scott's gone.
Okay, hold on.